Good day, my name is Roos, and today I'd like to talk to you about the work that we've done on the geometrical acceleration of complex equilibrium calculations for integration in high temperature models. Today I'd like to give a quick background on the industry that we are working in and the models we use, as well as the problems we are facing regarding the solving time of these models. Then I'd like to talk to you about the accelerator algorithm that we've developed to address this problem and present you with some performance results, after which I will close off with a short conclusion. So the pyrometallurgical industry that we are working in is the processing of minerals and materials at high temperatures. And it's these temperatures and the harsh environment that make it difficult to measure, monitor and analyze these processes. However, the products from these processes serve many other important industries, whether it's steel and any of its alloys, or exotic metals such as titanium or nickel, or even in the automotive industry, whether it is steel or aluminium for the chassis, or platinum and palladium used in the catalytical converters, or used in the electrical vehicle batteries to extend their range. The pyrometallurgical industry, however, is experiencing ever-increasing demands while having to be more energy efficient and reduce its environmental impact, while using ore that's becoming poorer and poorer in quality, and the process is becoming more complex as it's trying to incorporate recycling. The steel industry is a good example, where it is the second largest contributor of the global CO2 emissions, and governments are forcing emission reductions. This means that parts of the processes needs to be improved or redesigned, and this leads to the development of new technologies. So parts of the processes needs to be replaced, and some parts of these new processes do exist and are well understood, while the other parts do not exist yet and has to be designed, and there's still some uncertainty of how these processes should look like. The development has to be done on a strict deadline, which means that there might be time to build pilot plants, most probably not time to build demonstration plants. But what we can do is we can look at the thermochemistry, material properties and material characterization. We can do experiments and we can build multiphysics models. And what we want to do is we want to include thermochemistry and more detailed material properties into our multiphysics models. However, this at the moment is still unfeasible. Why do I say this is unfeasible? If we want to directly include thermochemistry into our multiphysics models, we look at the computational time of a single equilibrium calculation as the number of system components increase to be able to model more and more complex systems. And we can see for a 10 component system, a single equilibrium calculation time can take about 17 seconds. Now in a multiphysics model, we can have hundreds and thousands or millions of cells, and in each one of them we have to perform an equilibrium calculation, which means that a single iteration's computational time can become days, weeks, or even months. And if we want to perform multiple iterations to firstly reach convergence, or if it's a transient model, we are looking at total computational times of years. To address this problem, we wanted to develop an equilibrium calculation accelerator. So how will we interface with this accelerator? Well, we first look at the carbon and iron system as an example. The model will provide the accelerator with a specified independent system state, which consists of the composition as well as the non-compositional potentials, such as temperatures and pressures. And in return, the accelerator provides us with an equilibrium state, which can consist of the phase fractions of all the phases present at equilibrium, as well as the thermochemical and physical properties of the system. For each one of the phases, we also get equilibrium properties such as the composition of the phase, as well as the thermochemical and physical properties of each. This is done for every phase that is present at equilibrium. Before we developed the accelerator, we first set out some requirements. Primary of which is it had to work for any number of system components, it had to be thermodynamically consistent, use as little storage space as possible, and provide the user with control over the accuracy. But it also had to have high performance, support multiple applications, whether it's a process or a multiphysics model, and integrate with multiple free energy minimizers. So in brief, the accelerator algorithm. The algorithm takes advantage of the fact that the phase diagram is a geometrical representation of your system, and we can use tools such as the Gibbs phase rule to determine the dimensionality of the phase region boundaries, because their shape or dimensionality is governed by the Gibbs phase rule. If we look at the single phase region in this binary system as an example, the Gibbs phase rule tells us that the degrees of freedom is equal to 2, which means it's a 2D surface requiring 3 equilibrium calculations to discretize. So if we perform our 3 equilibrium calculations, we can combine them together and form an interpolation cell and store this to the accelerator's database for later recall. Similarly, if we look at the two-phase region in the same system, the degrees of freedom is calculated to be 1, which means that the phase region boundaries are 1D curves or lines, meaning that 2 equilibrium calculations are required to discretize the phase region boundaries. So if we perform our 2 equilibrium calculations, we can see the tie lines discretizes the phase region boundaries, and we can combine these two to create an interpolation cell, again storing this to the database for later recall. In a ternary system, we can look at the one-phase fraction, the one-phase region. The degrees of freedom is equal to 3, so it's a 3D volume or 3D boundary. If we look at the two-phase region, the degrees of freedom is equal to 2, so we have 2D phase region boundaries. And the three-phase region, the degrees of freedom is equal to 1, meaning that we have one-dimensional boundaries. By controlling how close or how far these tie lines are, or tie triangles are, before we combine them into an interpolation cell, we can control the level of accuracy of the interpolation we will have. So this method allows us to at least have control over the accuracy. So the Gibbs phase rule allows us to reduce the dimensionality of the features that needs to be discretized. So instead of discretizing the entire phase region, we only have to discretize the phase region boundaries, which means that the number of calculations are very small, which means that the data that has been generated and has to be stored is also small. The generality of the Gibbs phase rule also allows this discretization method to work for any number of system components. So now that we have our interpolation cells, we can look at how we perform interpolation in them. Firstly, looking at binary systems, the single phase region. If we have a specified system state, we first interpolate towards the temperature, and then we get these two nodes, and we can interpolate inwards to determine the equilibrium state. In a two-phase region, firstly we interpolate towards the temperature, and we get this interpolated tie line, and when we can use the lever rule to interpolate inwards and determine the equilibrium state. In a ternary system, first looking again at the single phase region, interpolate towards the temperature of the system state, and then we can interpolate inwards towards that to determine the equilibrium state. The three-phase region is again interpolating towards the temperature of the system state, and we can get this triangle, and then with the lever rule we can interpolate inwards and get the interpolated state. The two-phase region, however, is a little bit more difficult. So if we interpolate towards the temperature, we get this isothermal plane, and somewhere on this isothermal plane we have to calculate the position of the tie line that perfectly fits through the specified system state. So the interpolating algorithm that we've developed to perform this is generic, but however it is nonlinear and inefficient, but at least it is thermodynamically consistent, which means that the tie line that we've determined is always at the same temperature and chemical potential as the specified system state. The first industry relevant system that we tested the accelerator algorithm against was the ilmenite smelting system. Two important products of this process is titanium metal as well as white pigment that is used in a lot of everyday products. Being able to include the thermochemistry in the multiphysics models of this system will help us better understand the process as well as improve the smelter operation. 1 million specified system states were generated in temperature and compositional ranges associated with the molten metal and slag bath, as well as the interface between them. We can see the acceleration factor for all discretizations were less than 1, which is expected as an equilibrium calculation has to be performed, and there's additional overhead of finding the data of other equilibrium calculations to be combined into creating the interpolation cell. Interpolations show acceleration factors in the order of 10 to 100, with a few being as high as 1,000. We can see that initially the model is only discretizations being performed, and as the model progresses, more and more interpolations are performed, and this led to a model that potentially would have solved in 22 hours being solved in 15 hours. The errors made on phase compositions are shown on the left, and we can see at the 10 to the minus 16 mark, those are the errors made on compounds. And because compounds have a constant composition, no error is made, and that is simply due to the machine precision. The rest of the errors made are associated with the solution phases, and we can see that there's about a 1% error being made on the compositions. A maximum error of 1%. Because the phase fraction is dependent on the composition of the phases, the errors associated with the phase fraction is very similar to that as to the phase composition. Errors made on thermochemical properties. We can see that generally the errors made are about 1% and less, with the exception of some calculations in the single phase regions being about 10%. This is due to the non-linear variation of thermochemical properties with temperature and composition in these regions. The second industry-relevant system that we tested our accelerator algorithm against was a steelmaking system. Because it's important to us to understand the iron steelmaking system, it would be beneficial to us to be able to include thermochemistry into our multiphysics models. That will allow us to better understand and answer the questions regarding the changes that are being made to the industry. 1 million specified system states were generated in the temperature and compositional ranges associated with molten metal and slag baths, as well as the interface between them for both the iron making and steel making components of this process. Again, as in the ilmenite system, we can see that discretizations, the acceleration factor associated with discretizations are less than 1, and with the interpolations again in the order of 10 to 100, with some reaching 1,000. It can be seen again that as the model progresses, more and more interpolations are performed, and in this case a model that could potentially have been 30 hours has been reduced to 22 hours. The errors made on the phase composition, we can see again at 10 to the minus 16 is associated with the compounds, and the rest being associated with the solution phases, with an error of 1% and less being made on the composition. And again, the errors made on phase fraction being similar to that of the phase composition, seeing that it is dependent thereon. The thermochemical properties, the errors we are making there is again in general about 1% and less, apart from the single phase regions where some errors can be made up to 10%. So to conclude, the accelerator algorithm that we have developed work for any number of system components thanks to the inclusion of the Gibbs phase rule. It is thermodynamically consistent, and it uses as little storage space as possible, and it allows the user control over the accuracy. Although the performance has increased over the past year, there is still some room for improvement. It does not support multiple applications yet, and it does not integrate with multiple free energy minimizers. So we are getting closer to the stage where we can include equilibrium calculations in our models more efficiently, which will help us to gain insight into complex processes so that we can assist the pyrometallurgical industry with their challenges to better serve other important industries. Thank you.